Alright, so before I begin this video, a couple of disclaimers. First of all, this isn't going to be about my mega fave number. I've already made a video about that, you can see it in the description. But this is going to be about someone else's mega fave number, and that other person is Matt Parker. Second of all, I'm not an expert in this topic. No, I'm just trying to have a conversation about this. And plus, I didn't really prove any of these results either. These are just probabilistic ad hoc arguments that I'm giving, but I just wanted to share my thoughts. Alright, with that out of the way, let's hop into the video. So Matt Parker made a video about primes p, where the tan of p is bigger than p. And he talked about various ways to approach this problem, and they did find one example of a prime that satisfies this, and that number became Matt's mega fave number. And they asked the question, are there any other primes p that satisfies this? And what they guessed is that there was only one prime that satisfies this, which would make that number very special indeed. But today I'm going to give an argument that there are actually probably infinitely many primes p that satisfies this. Again, my argument could be wrong, and it probably is, but these are just my thoughts. So my argument really boils down to two key components. So let's suppose that n is a random positive integer. Now, what do I mean by a random positive integer? Well, there are various technicalities to this, but we're just going to assume that we're picking one positive integer at random, and we want to test a few properties of it. So the first main ingredient that we need is that the quote-unquote probability that tangent of n is bigger than n is roughly 1/pi(n). So this property is quite familiar. It's one of the properties that we want this number to be, but we also want it to be a prime, remember. So the second fact that we're going to use is that the quote-unquote probability that n is prime is roughly 1/log n. So this second fact is sometimes called the prime number theorem, and I'm not actually going to prove this in this video. The proof is quite complicated, so we're just going to take this second fact for granted. This first fact, though, is quite special to this problem, so half of this video is going to be about this first property, and then later we'll combine these two facts and sort of try to see why there are infinitely many primes p that satisfies this. Alright, let's try to find the quote-unquote probability that the tan of n is bigger than n. So first of all, what is this tan of n, right? Well, let's look at this graph of the tangent function. It's basically a bunch of infinite S-shaped curves like this in a repeating pattern. And so where do we find tan of n? Well, it's going to be somewhere along this x-axis. So it's going to be somewhere here, and this is going to be n. And so tan of n is just going to be the y value of this point, which is going to be something. And so the first assumption that we're going to make is that we're going to assume that this probability is going to be equal to the probability that the tan of a random angle is greater than n. Now this step might be kind of iffy, but I think it's sort of a fair assumption to make because we really don't know anything about this tan function and its period. Alright, so if we're going to assume that this is going to be a tan of a random angle is bigger than n, then, well, to make things easier to work with, we can assume that we just have an angle between -pi/2 and pi/2, because it sort of repeats anyways. So we're going to pick an angle basically on only one of these infinite curves, so just this middle one, I guess. And we're going to pick a random theta from this interval, and we're going to say that this probability is just the probability that tan of theta is greater than n. Alright, now how do we find this probability? Well, let's think about what it means for tan of theta to be bigger than n. So let's look at this graph. This is the graph of the tan function from negative pi over 2 to positive pi over 2. And so we get this S-shaped curve. Now, what does it mean for tan of theta to be greater than n? Well, that basically means that theta has to be between this very small interval here. If theta is in this tiny interval, then tan of theta is going to be over here, and so that would mean that tan of theta is bigger than n. And if theta was anywhere here, then tan of theta would be less than n. So to find the probability that tan of theta is bigger than n, we need to find the probability that if we pick a random value of theta, that it will just happen to land in this small interval. And how do we do that? Well, we'll first have to find the length of this interval, and then we'll have to divide it by the length of this entire interval. And how do we find the length of this tiny interval? Well, we can take this right endpoint, which is pi over 2, and subtract this left endpoint. Now, what is this left endpoint going to be? Well, it's actually going to be the inverse tangent of n, right? Because this is the tangent function, so if this is n, then the x value is going to be the inverse tangent of n. So the length of this tiny interval is going to be pi over 2 minus this tan inverse of n. And the length of this whole interval, well, that's pi over 2 minus negative pi over 2, which is just pi. So we end up getting an expression like this. All right, now we're going to use a famous fact from trigonometry, the fact that the tangent inverse of n plus the tangent inverse of 1 over n equals pi over 2. Now, this is quite a famous fact of trig, but if you haven't seen this fact before, I'll give a quick argument for why this is. So let's look at this triangle here. It's a right triangle, and the legs are length 1 and n. So this top angle here, what is this top angle? Well, we don't know that, but we do know that the tan of this top angle is going to be equal to the opposite side over the adjacent side. So it's going to be n over 1. So the tan of this angle is going to be n. So this angle here is actually just the inverse tangent of n. So that's that first term. And you can use a similar argument to show that this angle here is going to be the tangent inverse of 1 over n. And you know that the sum of the angles of a triangle is always going to be 180 degrees, which is pi. And so since this third angle is a right angle, which is just pi over 2 radians, then you know that the sum of these two angles must be pi over 2. All right, so if this equation is true, then let's take the inverse tan of n and move it to the other side. So we get this expression here. Inverse tan of 1 over n is equal to pi over 2 minus inverse tan of n. Now we can substitute this into this expression here, and we would end up with an expression like this. We just took the tan inverse of 1 over n and sort of substituted it in for here, replace this with this. All right, so now we're going to use a famous fact from calculus. But if you don't know calculus, it's okay, because you can understand this fact without knowing calculus. But it's essentially that if x is small, then the inverse tan of x is roughly x. And you can see this by looking at this graph of the inverse tan of x. So here we have the line y equals x, and here we have the line y equals tan inverse of x. And you can see that these lines are really close at values around 0. And if you know a bit of calculus, then you can show that this approximation is really good, because the second order derivative is 0. So if this is true, then the inverse tan of 1 over n is going to be roughly 1 over n, because we're assuming that n is fairly large, so we're going to be assuming that 1 over n is fairly small, so we're going to be assuming that this approximation is fairly accurate. So we're going to say that this is roughly 1 over n over pi. And so we get our expression that we were looking for of 1 over pi n. All right, so we just gave an argument for this first fact here. And remember, we're taking the second fact for granted. And remember what we're trying to do with this. We're trying to find numbers n where n is prime and the tan of n is bigger than n. So we can use these two statements to find that the quote-unquote probability that both tan of n is greater than n and n is prime is going to be the product of these two probabilities. Remember that if we take the and of two things, then that probability is going to be the product of the probabilities of these two things. So we're going to get, it's approximately 1 over pi n log n. So remember, we claimed at the beginning that there are infinitely many numbers that satisfy these two properties. And the way we're going to show this is we're going to find the quote-unquote expected number of positive integers n, where tan of n is bigger than n and n is prime. And the way that we're going to do this is we're going to add up the probabilities that each positive integer satisfies both of these two probabilities, and that's going to give us an approximation for the expected number of positive integers n that satisfy these properties. So if we write out this sum, we're going to get an expression like this: 1 over pi times 2 log 2 plus 1 over pi times 3 log 3 plus 1 over pi times 4 log 4, and so on. I might notice that we skipped 1 over pi times 1 log 1, but that's because log 1 is 0 and we can't divide by 0. So that's a small technicality, but I mean 1 isn't prime, so we don't really have to consider it. Now, how do we evaluate this infinite sum? Well, first off, we can factor out the 1 over pi, right? That can make things a bit easier. And we can convert this to a sum notation by writing it as 1 over pi times the sum from n equals 2 to infinity of 1 over n log n. All right, now it all comes down to evaluating the sum from n equals 2 to infinity of 1 over n log n. Now, this next part is actually going to involve quite a bit of calculus. So if you don't know calculus, you'll just have to take my word for it here. But if you do know calculus, I think you'll find this argument pretty cool. So what we're going to use is something called an integral test. So we're going to say that this sum is greater than this integral of the same thing. So remember, instead of 1 over n log n, we'll put 1 over x log x. And we're integrating from 2 to infinity. And this works because 1 over x log x is a decreasing function, which is why we can use the integral test here. Now, how do we evaluate this integral? Well, first off, let's rewrite it like this. Integral from 2 to infinity of 1 over log x times 1 over x dx. And now what we're going to use is a u substitution. So we're going to use u equals log x, and then if we differentiate both sides, we get that du equals 1 over x dx. So if we plug these into here, then the expression we get is just the log x becomes u, 1 over x dx becomes du, and we get this expression. Of course, the bounds are changed. This is now log 2, and the infinity, well, it becomes log infinity, but the log of infinity is still infinity. But now this is an integral that we can actually evaluate, and namely, this is just the natural log. So we can write this as the log of u evaluated from log 2 to infinity. And if we were to evaluate this, we would get log of infinity which is infinity, minus log of log 2, which is some number. And so we would get infinity. So we end up getting that this integral is equal to infinity. But remember that this sum must have been greater than this integral. So we can safely conclude that this sum is equal to infinity. Well, remember this expression that we got for the expected number of numbers of this form? Well, we just found out that this sum is actually going to be equal to infinity. So 1 over pi times that is still going to be equal to infinity. So we would expect that there are infinitely many numbers n that satisfies these two properties. Now there are quite a few assumptions that I made in this video. The first assumption is that pi and the primes are both random, quote unquote. And the second assumption is that we assume that pi and the primes aren't related to each other. Remember, that's why we could take these two probabilities, one involving pi and one involving the primes, and sort of just multiply them as if they're just independent things and just get the probability that both of these are true. So we're assuming that pi and the primes are independent, but we have seen relationship before between pi and the primes. So this assumption is pretty bold. Also, this assumption that we made, that the probability that tan of n is greater than n is the probability that the tan of a random angle is greater than n, this assumption is pretty bold too, because even though pi is random, the integers are not. So this assumption isn't entirely clear. But if we do assume that these things are random enough, then we do get this result. So until someone proves me wrong, this is going to be my opinion that there are indeed infinitely many primes that satisfy tan of p is bigger than p.